Thank you very much. Okay. Thank you. Yeah, thank you very much for having me here. I would now like to give you some insight into what I think is a very fascinating ant plant mutualism. And this is based on research that I have done together with colleagues in the Kenyan savannah. Living there can be dangerous, not necessarily for me, but for trees. Because the elephants can have a devastating effect on the growth and reproduction rate of trees. There is one tree, however, that is rarely touched by elephants, and that is a whistling thorn acacia tree. And this tree employs ants as bodyguards for their protection. So once a tree is under attack, the ants quickly emerge from their plant shelter, swarm all over, as you can see over my arm, or into an elephant's trunk, and then bite or chase away the intruder. And this is very effective and has been studied for long. But there's one tiny little bit that has not been known until recently, and that is how the ants actually get informed about the attack. So in a situation like this, time is crucial. A single ant just can't fight away Goliath. But as many ants as possible have to be informed as soon as possible. And that is not easy if you consider that most of the ants actually hide inside these bulbous thorns. So they neither see nor do they smell the elephant. So their best bet, what we thought, was if they would rely on their sense of vibration. Because, after all, a tree vibrates if an elephant nibbles upon it, and these vibrations spread very quickly all over. So this is what we wanted to study. But working with elephants and delicate measurement equipment was not really an option, because elephants are very gentle, but just not gentle enough. So what we did was employ a goat that would nibble in a very similar way. And we could then measure these vibrations. And this is what a frequency spectra looks like. So it's very broadband and has frequencies of up to 6 kilohertz. This is very much in the range of what ants can detect. And then you might say, well, a tree does not only vibrate when it is nibbled upon, but also when the wind blows, and true that. So we also had to measure the vibrations that are caused by wind. And we did that and see some differences. So the vibrations which are induced by wind are lower in amplitude, and they also have a lower frequency range. So we can see these differences. The question was whether the ants can also detect these differences. What the ants definitely can do is chase away goats. So each arrow here indicates a single ant that gave our goats a really hard time. Such a hard time that they simply refused to work and quit the job. So we had to come up with an alternative. And that was something we called an artificial browser. It was, without any complaint, work in a very reproducible manner with very short vibrational pulses. And it was acting like a goat or like a browser, but not like a wind. So exactly what we wanted. So again, the question is, do ants see the difference between these two vibrations? So what we did is observe their behavior, the behavior in case of wind shaking the tree. And we found that the activity was not affected. When the tree vibrates as if it was nibbled upon, we find an increase of that activity. So in other words, when the wind blows, they're not bothered. They just stay inside of their thorns, and that's it. But if an elephant is there, if an elephant nibbles on it, they quickly emerge from their plant shelter and move all over in search for that enemy. Now this graph shows how these vibrations spread over the tree. So close to the point of impact where the elephant is, where the nibble is, the amplitude is very high, indicated by red. And then it gets weaker, of course, the way it spreads, and turns from red towards blue. But even though it gets weaker, it can still, on the other side of the tree, be detected by ants. It's still strong enough. And it is not only strong enough, but it is also that the ants on the spot can tell where they have to go, where the source of vibration is. So in a control experiment, the ants would just move randomly, left or right, doesn't matter. But as soon as we introduced vibrations, they would predominantly walk towards the source of vibration, Or in other words, to the elephant, to the front line to attack and chase away whoever is disturbing their tree. And what I have just told you, that the wind does not make a difference for the protective behavior of the ants, the wind might actually be crucial for the attacking elephant, because it seems as if the tree and the ant together employ the wind as an early warning system that is based on sound, actually. And you can't imagine now like a shrilling siren, but rather a whistle, because I mean, the whistling thorn acacia, the name says it, it whistles. And to understand, so it whistles, and it whistles because the wind blows over it and because the ants have drilled a hole inside of this thorn. So the whistle indicates there are ants and how they're going to defend this tree. So it would be very beneficial if the elephants or whoever wants to attack that tree would make use of this alarm signal. And for the ants in the tree, it would be beneficial if as many thorns as possible would whistle as loud as possible. To see whether this is the case, we, in the next step, had to understand the whistle a bit better and the wind better, and also then the behavior of the ants. So the first thing was to construct a wind channel, and with this we figured that the thorn actually acts like an Helmholtz oscillator, similar to these bottles. So as you may well know, the angle at which the air strikes over the bottle opening is crucial for sound production. And if you just do it in the wrong way, you won't create a sound. And the same is true for the thorns. So it matters. If they have to be exposed towards the wind, and ideally in an angle of 45 degrees. So again, it would be nice if the thorns on a tree would then be exposed toward the wind direction, and I'm running away from you, toward the wind direction. So we the next step, took a look at the wind direction we would have at our study site, and we found that the wind predominantly blows from southeast. So we would now, in the next step, think, so ideally the thorns would then also face southwest, right? So we went out to the field and simply checked in what directions do the hole openings face. And we probed like 600 thorns and found that indeed, predominantly, all the thorn openings face the windward direction. And this very much supports our hypothesis, and I hope you're as excited I am that this is what is probably the first acoustic episomatic warning signal of a plant. Thank you very much. Thank you to all the people, all the goats, and all the institutions, and you.